settle into the sleepy mind channel. Tonight we will travel across some of the coldest and most remote places on Earth to explore the hidden world of ice and glaciers. From the towering ice fields of Antarctica and Greenland to the frozen valleys of Alaska, Iceland, Norway, and the Himalayas, glaciers have been slowly forming for thousands of years, long before modern cities, roads, or even written history existed. Some of these frozen landscapes are so isolated that very few people will ever see them in person, while others have become famous destinations where travelers stand beside glowing blue ice, frozen lakes, and enormous drifting icebergs. Yet even in the places people visit every year, glaciers still hold mysteries hidden deep beneath their surface, preserving ancient snowfall, trapped air from distant ages, and clues about the changing history of the Earth itself. If you enjoy calm videos like these, feel free to like and subscribe. More videos are posted weekly, and for more interesting topics designed for all-night listening, feel free to explore the playlist after tonight's journey. Let us begin. Most people think of glaciers as frozen landscapes that simply sit in silence at the edges of the world. They picture distant mountains, white fields of snow, or enormous walls of blue ice drifting quietly beneath grey skies. Yet glaciers are more active than they appear. Beneath their still surface, landscapes are slowly being shaped, crushed, scraped, carved, and moved across the Earth with such patience that the movement is almost impossible to notice in a single human lifetime. A glacier may appear motionless during an afternoon walk, or even during the course of many years, but in reality, it is always changing. Deep inside the ice, pressure builds, layers shift, and gravity quietly pulls vast frozen masses across valleys and mountains with slow but unstoppable force. Some glaciers are older than entire civilizations. Snow that once fell onto cold mountain peaks long before the rise of modern cities can still remain trapped deep within the ice today. Tiny particles of dust from ancient storms, traces of old volcanic eruptions, and even bubbles of ancient air can remain sealed beneath layer after layer of compressed ice for thousands of years. In many ways, glaciers act like frozen libraries. Instead of storing books or written records, they store evidence of the Earth itself. Each layer preserves a small piece of environmental history. Scientists who study glaciers are often studying time as much as they are studying ice. The strange thing about glaciers is that they behave unlike almost anything most people encounter in daily life. Ice inside a glacier can appear solid and rigid, yet over time it behaves more like an extremely slow-moving river. Imagine a thick drop of honey sliding across a plate so slowly that its movement could barely be detected from one day to the next. A glacier moves with a similar kind of patience, though on a scale so enormous that entire valleys can eventually be reshaped beneath it. Mountains can be carved into new forms. Rocks can be carried across great distances. Deep scars can be cut into Earth's surface, leaving behind wide valleys and steep cliffs that remain visible long after the ice itself disappears. In some parts of the world, glaciers once covered areas larger than modern countries. During colder periods in Earth's history, enormous ice sheets stretched across continents and slowly transformed the land beneath them. Places that are now forests, towns, farms, and busy roads were once buried beneath thick layers of moving ice. The marks left behind by these ancient glaciers still exist today, though many people pass them without realizing it. Certain lakes, valleys, hills, and plains were all shaped by the slow pressure and movement of ice over time. Even now, glaciers continue to influence rivers, oceans, landscapes, and climate systems across the planet. The story of a glacier begins with something very small and familiar. Snow falls quietly onto cold ground. One winter passes, then another. More snow arrives each year, and in places where the cold remains strong enough, the older snow never completely melts away. Fresh layers slowly bury the older layers beneath them. Over time, the growing weight of accumulated snow begins to press downward. Air spaces between snowflakes become smaller. Loose snow becomes tightly packed together. Gradually, the texture changes from soft powder into dense grains of ice. The process happens slowly enough that no clear dividing line exists between snow and glacier ice. Instead, the transformation unfolds over years through steady pressure and deepening weight. Most people experience snow as temporary. A snowfall may last for a few days before sunlight, rain, or warmer temperatures erase it from the landscape. Glaciers exist in places where winter gains a small advantage each year. More snow arrives than disappears. Even a slight imbalance can slowly build enormous masses of ice over time. A single season may not seem important on its own, but glaciers are built through accumulation across centuries. The ice inside some glaciers today may contain snowfall that landed on the Earth during periods of history so distant that entire generations have come and gone, while the glacier quietly continued to grow. As snow becomes buried beneath newer layers, pressure increases deeper within the glacier. Individual snowflakes lose their delicate shapes and become compacted together into dense crystalline ice. The trapped air between them becomes squeezed into tiny pockets. The deeper the layers sink, the heavier the pressure becomes. Eventually, the ice grows thick enough and dense enough to behave as a glacier rather than a simple layer of frozen snow. From above, the surface may still appear calm and silent, but deep beneath the top layers, the glacier has already begun its slow transformation into a moving mass shaped by gravity and time. The color of glacier ice often surprises people who see it for the first time. Instead of appearing white like ordinary snow, thick glacier ice can glow with deep shades of blue. This color develops because dense ice absorbs more red light while allowing blue light to pass through. The effect becomes stronger in thicker and older sections of the glacier where the ice has become tightly compressed over time. Large cracks, caves, and exposed walls of glacier ice can sometimes appear illuminated from within, almost like frozen glass lit by hidden light beneath the surface. In quiet polar regions and mountain valleys, these glowing blue formations can seem almost unreal against the surrounding snow and rock. Although glaciers form in extremely cold environments, temperature alone does not determine whether a glacier can survive. What matters most is balance. Snowfall must continue adding more ice than melting removes. If too much ice melts during warmer seasons, the glacier slowly shrinks. If snowfall continues building faster than melting occurs, the glacier can continue growing thicker and larger over time. This balance between accumulation and melting controls the life of every glacier on Earth. Some glaciers remain relatively stable for long periods, while others slowly advance or retreat depending on changing conditions. The hidden world inside a glacier is more dynamic than most people realize. Deep cracks can open across the surface as the ice slowly bends and stretches over uneven ground. Meltwater may travel downward through narrow shafts inside the glacier, carrying water deep beneath the ice. In some places, entire rivers can flow underneath glaciers, hidden from view beneath hundreds of feet of ice and snow. Far below the surface, pressure, movement, temperature, and gravity continue shaping the glacier every moment, even though the changes unfold with such slowness that they often escape human notice entirely. Deep within a glacier, the ice slowly changes as more weight presses downward from above. Fresh snowfall may appear soft and light when it first settles onto the surface, but over time, the lower layers become buried beneath enormous pressure. The deeper the snow sinks, the more tightly compressed it becomes. Tiny air spaces that once existed between individual snowflakes begin to shrink until the snow gradually transforms into dense crystalline ice. In some glaciers, this ice may eventually become hundreds or even thousands of feet thick. At those depths, the pressure becomes hard to imagine. The weight pressing downward can equal millions of tons spread across the ice, all slowly compacting the ice layer by layer over long stretches. The process happens so gradually that no single moment exists when snow suddenly becomes glacier ice. Instead, the change unfolds through many stages. Fresh snow begins with delicate flakes filled with trapped air. As more snow arrives, the lower layers are squeezed together until the flakes lose their original shape. The snow becomes grainy and compacted, almost like tightly packed sugar. Scientists often compare this intermediate stage to coarse crystals rather than soft snow. With enough continued pressure, those grains slowly fuse together into dense blue ice. What began as light snowfall drifting quietly from the sky eventually becomes part of an enormous frozen mass capable of shaping mountains and valleys. The environments where glaciers form are among the coldest places on the planet, though cold alone is not always enough to create them. Large amounts of snowfall are equally important. A dry frozen desert may remain extremely cold for long periods, while still lacking the snowfall needed to build glaciers. By contrast, some mountain regions receive heavy snowfall each year, allowing thick ice to slowly accumulate despite occasional warmer seasons. This balance between temperature and snowfall controls where glaciers can survive. Conditions must remain cold enough that more snow is added during winter than is lost during warmer periods. Even a small yearly surplus can gradually build immense glaciers over centuries. High mountain ranges often provide the perfect environment for glacier formation because temperatures remain colder at higher elevations. Moist air rises along mountain slopes, cools, and releases snow across peaks and valleys. Over long periods, snowfields in these cold regions may begin developing into glaciers as the lower layers compress into ice. Some of the most famous mountain glaciers exist in places like the Alps, the Himalayas, Patagonia, and the coastal mountains of Alaska. In these regions, glaciers may slowly flow down mountain valleys while fresh snowfall continues feeding the upper sections each year. Polar regions also contain some of the largest glaciers and ice sheets on Earth. Antarctica alone holds an extraordinary amount of frozen water locked within its massive ice layers. In some places, the Antarctic ice sheet reaches thicknesses greater than many mountain ranges are tall. Greenland contains another enormous ice sheet covering most of the island beneath a vast frozen cap. These polar glaciers formed through accumulation over extremely long periods, with snowfall gradually building layer upon layer while cold conditions prevented large-scale melting. If all the ice stored in Greenland and Antarctica were somehow melted, global sea levels would rise dramatically across coastlines around the world. Despite their frozen appearance, glaciers remain highly sensitive to conditions. A slight increase in average temperature can slowly shift the balance between snowfall and melting. Warmer summers may remove more ice than winter snowfall replaces. Reduced snowfall can also weaken glacier growth even when temperatures remain cold. In some regions, glaciers that once expanded steadily for centuries have begun shrinking because the balance between accumulation and melting has changed. These changes are clearest in photographs taken decades apart. The upper areas of a glacier where snowfall continues building are often called accumulation zones. In these colder regions, snow survives each year and slowly feeds the glacier with fresh material. Lower sections of the glacier may experience greater melting during warmer seasons. These lower areas lose ice through melting, evaporation, or the breaking away of icebergs where glaciers meet the ocean. A glacier survives only when the upper regions continue replacing the ice lost farther below. Glaciers behave like changing systems with cycles of gain, movement, and loss. Many people imagine glaciers as perfectly silent places, yet glaciers often produce a surprising range of sounds. Ice may crack sharply as pressure shifts deep within the glacier. Meltwater can rush through hidden tunnels beneath the surface. Large pieces of ice sometimes break away, with sounds similar to distant thunder echoing across valleys or polar seas. In colder regions during still nights, the slow expansion and movement of ice can create strange groaning or creaking noises that travel long distances through the ice. These sounds are reminders that glaciers are not motionless objects, but changing masses shaped by gravity, pressure, temperature, and time. One of the most surprising facts about glaciers is that they do not remain fixed in place. Although they appear solid and motionless from a distance, glaciers are constantly moving across the land with extraordinary slowness. This movement happens so gradually that a person standing beside a glacier would rarely notice any visible change during a single day. Yet over months, years, and centuries, glaciers can travel remarkable distances through valleys, across plains, and down mountain slopes. Entire rivers of ice slowly advance through the land under the quiet influence of gravity, carrying enormous weight with them as they move. The force responsible for this movement is simple and familiar. Gravity pulls everything downward toward the earth. Rainwater flows downhill through streams and rivers. Loose rocks tumble from steep cliffs. Snow slides down mountainsides during avalanches. Glaciers respond to the same force, though their movement unfolds at a vastly slower pace. A glacier perched high within a mountain range experiences constant pressure from the immense weight of the ice above it. Over time, gravity gradually pulls the entire frozen mass downhill. The movement may only measure a small distance each day, but the glacier never fully stops as long as enough ice continues feeding it from above. To understand glacier movement, it helps to stop thinking of glacier ice as something completely rigid like stone or metal. Instead, glacier ice behaves more like an extremely thick and slow-moving material. Scientists often compare glacier flow to substances such as honey, warm wax, or thick syrup moving very slowly across a surface. If a spoonful of honey is poured onto a plate, it may appear still at first glance, Yet over time, the honey slowly spreads outward under its own weight. Glacier ice behaves in a somewhat similar way, though the process unfolds across enormous distances and over far longer periods. Even solid ice can slowly bend and flow when exposed to enough pressure over centuries. Deep within a glacier, the pressure from the overlying ice becomes immense. This pressure allows the ice crystals inside the glacier to gradually shift position and deform. Individual crystals may slowly slide past one another or change shape under stress. Scientists describe this process as internal deformation. Instead of breaking apart completely, the ice adjusts itself gradually while still remaining connected as a single frozen mass. The movement happens continuously across the glacier, especially in deeper sections where pressure is greatest. Although the glacier appears stable from the outside, countless tiny shifts are constantly unfolding within the ice itself. The center of a glacier usually moves faster than the outer edges. Friction along the valley walls slows the sides of the glacier as they scrape against surrounding rock. The bottom of the glacier may also move more slowly because of contact with the ground beneath it. The result can resemble the movement of a river, where water near the center often travels more quickly than water along the banks. This uneven movement creates stress throughout the glacier, causing cracks called crevasses to open across the surface. Some crevasses remain narrow and shallow, while others can become deep enough to swallow much snow and ice far below the surface. Crevasses often appear in areas where glaciers travel over steep slopes or uneven terrain. The upper surface of the glacier may stretch and fracture as the ice moves over ridges or bends through valleys. In colder regions, fresh snowfall sometimes hides these openings beneath thin snow bridges that can appear deceptively solid from above. Explorers traveling across glaciers must move carefully because hidden crevasses can pose serious danger. In some parts of Antarctica and Greenland, crevasses may extend hundreds of feet downward into brilliant blue ice, illuminated by filtered sunlight from above. Another important form of glacier movement occurs at the base of the ice itself. In some glaciers, pressure and friction create small amounts of meltwater beneath the glacier, even when surrounding air temperatures remain extremely cold. This thin layer of water can act almost like a lubricant between the glacier and the ground below. Instead of moving only through internal deformation, sections of the glacier may slowly slide across the underlying rock. Scientists call this process basal sliding. The combination of internal deformation and sliding allows glaciers to travel across landscapes while carrying immense amounts of ice, rock, and sediment with them. The speed of glacier movement varies enormously depending on temperature, slope, ice thickness, and the amount of meltwater beneath the glacier. Some glaciers move only a few inches each day, while others can advance much more quickly under certain conditions. A few rare glaciers, known as surging glaciers, may suddenly accelerate for short periods before slowing again. During these surges, glaciers that normally move gradually can rapidly push forward across the land. Entire valleys may shift beneath advancing walls of ice, while cracks and pressure ridges form across the glacier surface as the frozen mass adjusts to the sudden increase in motion. Even the largest glaciers on Earth are constantly shaped by movement. Massive ice streams within Antarctica slowly transport ice from the interior of the continent toward the coast. Some of these frozen rivers are hundreds of miles wide and move steadily toward the surrounding ocean. From space, scientists can observe these enormous flows stretching across the Antarctic landscape like slow-moving highways of ice. The movement unfolds across vast distances and ages. Mountain glaciers create a very different appearance, though the same physical forces remain at work. In places like the Alps or the Himalayas, glaciers often wind through narrow valleys between towering peaks. The ice may curve around bends in the mountainside, while carrying crushed rock and debris along its surface. During warmer seasons, streams of meltwater sometimes flow beside the glacier or disappear beneath it through hidden tunnels carved into the ice. Despite the dramatic scenery, the glacier itself continues its slow downward movement every moment of every day under the steady pull of gravity. Although glaciers move with extraordinary slowness, their movement never truly stops. Day and night, through winter storms and summer sunlight, glaciers continue shifting across the land under the constant pull of gravity. Even when temperatures fall far below freezing and the surface appears perfectly still, the deeper layers of ice remain under pressure and continue flowing gradually forward. The movement may only amount to a small distance within a single day, yet over years and centuries the glacier can travel far enough to reshape entire valleys and coastlines. In many ways, glaciers exist within a different sense of time from ordinary human life. Their changes unfold slowly enough that generations may pass before the full effects become obvious. The speed of glacier movement depends heavily upon surrounding conditions. Temperature plays an important role because slightly warmer ice tends to deform more easily under pressure than extremely cold ice. The amount of meltwater beneath the glacier can also influence movement. When meltwater collects along the base, the glacier may slide more freely across the ground beneath it. The steepness of the landscape matters as well. A glacier resting on a gentle slope may move very slowly, while a glacier descending through a steep mountain valley can advance at a faster pace as gravity pulls more strongly downward. The thickness of the glacier also affects how it moves. Larger glaciers contain far greater weight pressing downward through the ice. This pressure increases internal deformation deep within the glacier and can produce steadier movement across long distances. Smaller glaciers may respond more quickly to seasonal changes, while enormous ice sheets often move with slow consistency over vast areas. In Antarctica and Greenland, some glaciers are so large that their motion resembles the gradual shifting of continents rather than the movement of ordinary rivers or streams. Scientists place markers across the ice to measure glacier travel. In some regions, stakes drilled into the glacier may slowly shift position each year as the ice beneath them flows downhill. Modern satellites now allow researchers to observe glacier movement from space with remarkable precision. By comparing images collected over time, scientists can detect subtle changes in glacier speed, thickness, and direction that would otherwise remain invisible to the human eye. These measurements help researchers understand how glaciers respond to changing conditions. In colder mountain regions, glacier movement can sometimes produce visible effects upon the surface of the ice itself. Long cracks may widen as different sections of the glacier travel at different speeds. Curving bands of crushed ice known as ogives can form below steep ice falls where glaciers descend rapidly over uneven terrain. Dark stripes of rock debris may appear along the glacier surface where material from valley walls becomes trapped within the flowing ice. These patterns reveal that the glacier is not simply a frozen block resting in place, but a constantly moving system shaped by pressure, terrain, and gravity. Some glaciers flow so steadily that forests, rocks, and even old paths beside them gradually change position relative to the ice over time. Historical photographs taken decades apart often reveal dramatic shifts in glacier location that would be impossible to notice during a short visit. Valleys once filled with thick ice may slowly become exposed as glaciers retreat, while advancing glaciers in colder periods can gradually spread farther into surrounding landscapes. Entire lakes may form where retreating glaciers leave depressions behind, creating new environments long after the ice itself has moved away. The shape of the land beneath a glacier strongly influences how the ice behaves. Narrow valleys can funnel glaciers into long flowing tongues of ice that travel downhill between steep mountainsides. Wide open regions may allow glaciers to spread outward more gradually across broad landscapes. Rocky ridges beneath the glacier can create pressure zones where cracks develop across the surface. In some places, glaciers flow over cliffs or steep slopes, causing the ice to fracture into towering blocks and chaotic frozen formations called ice falls. These areas can resemble frozen waterfalls suspended in motion across the mountainside. Gravity remains the driving force behind every stage of glacier movement. Without gravity pulling the ice downhill, glaciers would simply accumulate in place rather than flow across the land. The greater the mass of the glacier becomes, the stronger gravity acts upon it. Even relatively small glaciers contain tremendous weight pressing downward through the ice. This constant force slowly overcomes the resistance within the glacier, allowing the frozen mass to continue advancing through valleys and across plains over time. As glaciers move across the land, they do more than simply travel from one place to another. Over long periods, glaciers actively reshape the land beneath them through enormous pressure and constant friction. Mountains, valleys, cliffs, and plains can all be altered by the slow passage of ice. Unlike rivers, which carve narrow channels through flowing water, glaciers transform regions at once. Their immense size allows them to grind against the earth with extraordinary force, gradually wearing away rock surfaces and carrying material across great distances. The effects may unfold slowly, but glaciers remain among the most powerful landscape-shaping forces on the planet. One of the reasons glaciers are able to reshape terrain so effectively is because they rarely move alone. As glaciers travel, they collect rocks, gravel, sand, and sediment from their surroundings. Some of this material falls onto the glacier from nearby cliffs and mountainsides. Other pieces become frozen into the ice as the glacier moves across the ground below. Over time, glaciers can accumulate enormous amounts of embedded rock throughout both their surface and deeper internal layers. Glaciers can behave like giant conveyor belts, carrying crushed stone across the land. The weight of a glacier pressing downward is already immense on its own, but the addition of embedded rocks transforms the glacier into something even more powerful. Sharp stones trapped beneath the ice are dragged across the ground as the glacier moves forward. This constant scraping gradually grinds against exposed bedrock below. Scientists call this process abrasion. The effect can be compared to sandpaper rubbing repeatedly across a wooden surface, though glaciers operate on a far larger scale and over much longer periods of time. Instead of smoothing furniture or shaping small objects, Glaciers slowly polish mountains, deepen valleys, and scrape broad sections of the Earth itself. The surfaces left behind by abrasion often display visible marks showing the direction the glacier once traveled. Long scratches and grooves called striations can remain carved into exposed rock after the glacier retreats. These marks act almost like signatures left behind by the moving ice. Scientists studying ancient glacial landscapes often examine these scratches to understand how glaciers moved across the region thousands of years ago. In some places, entire rock surfaces appear polished smooth after centuries of grinding beneath thick, moving ice. The grinding force beneath a glacier can be difficult to imagine because glaciers move so slowly, yet the enormous weight involved changes the scale entirely. A thick glacier may contain billions of tons of ice pressing downward against the ground below. Even slight movement under such pressure becomes incredibly powerful over time. The embedded rocks act like cutting tools trapped beneath the glacier, continuously scraping the landscape each year. Small changes accumulate slowly until valleys become deeper, hills become smoother, and entire mountain regions are gradually reshaped. Glacial abrasion can also produce extremely fine rock particles known as rock flour. As the glacier grinds against bedrock, countless tiny fragments are crushed into powder beneath the ice. Meltwater streams flowing from glaciers often carry this fine sediment downstream, giving glacial rivers and lakes a cloudy blue or grey appearance. In places such as Alaska, Patagonia, and parts of the Canadian Rockies, glacial lakes sometimes glow with bright turquoise colors created by suspended rock flour reflecting sunlight through the water. The striking color that visitors admire in these lakes is often the result of countless years of slow grinding beneath nearby glaciers. Mountain glaciers provide some of the clearest examples of abrasion in action. As glaciers descend through narrow valleys, they scrape against both the valley floor and surrounding walls. Sharp ridges may become smoothed and widened through repeated contact with the moving ice. Jagged rocky terrain gradually transforms into broader and more rounded forms. Over long stretches of time, glaciers can carve landscapes that appear very different from those shaped primarily by rivers or weather alone. The lower sections of glaciers often contain the greatest concentration of embedded rocks, because this is where the ice remains in constant contact with the ground beneath it. Large boulders may become frozen into the base of the glacier and dragged slowly across the land for many miles. Some rocks carried by glaciers eventually end up deposited far from their original location after the ice melts away. Scientists sometimes identify these transported boulders, known as glacial erratics, sitting in regions where the surrounding rock type is different. These misplaced stones provide evidence of how glaciers once traveled across ancient landscapes. Abrasion does not occur evenly across every glacier. Some glaciers move over softer rock that wears away more easily, while others travel across harder surfaces that resist erosion for longer periods. Temperature also matters because glaciers with meltwater beneath their base often slide more efficiently, increasing the grinding effect against the landscape below. Steeper slopes may produce greater movement and stronger erosion, while flatter terrain may slow the glacier and reduce the intensity of abrasion. Glaciers do not only grind and polish the land beneath them, they can also tear enormous pieces of rock directly from the earth itself through a process known as plucking. While abrasion slowly scrapes surfaces smooth, Plucking works in a more dramatic way. As glaciers move across uneven terrain, meltwater can seep into cracks and fractures within the underlying rock. When temperatures fall, that water freezes and expands inside the cracks. Over time, pieces of rock loosen from the surrounding surface. As the glacier continues moving forward, the ice may freeze around those loosened sections and pull them away from the ground entirely. The process happens gradually, though the results can be enormous. Small fractures may slowly widen across many years until large blocks of rock become unstable beneath the glacier. Eventually, the moving ice grips these weakened sections and tears them free from the landscape. Some of the rocks carried away by glaciers can be extremely large, weighing many tons. Once trapped within the ice, these rocks may continue traveling with the glacier for miles before finally being deposited elsewhere after the ice melts away. Plucking is especially common in mountainous regions where exposed rock surfaces contain many natural cracks and fractures. Mountain glaciers flowing through steep valleys often encounter uneven terrain filled with ridges, cliffs, and broken stone. Meltwater generated beneath the glacier seeps into these openings before freezing again during colder conditions. The repeated freezing and expansion slowly weakens the rock structure over time. The glacier then acts almost like an enormous hand pulling pieces of the mountain away as it advances downhill. Together, plucking and abrasion allow glaciers to reshape landscapes with remarkable effectiveness. Abrasion smooths and grinds surfaces, while plucking removes larger sections of rock entirely. The combination gradually transforms rough mountainous terrain into broader valleys and steeper cliff faces. Areas once shaped primarily by rivers may slowly take on different forms after long periods of glacial activity. Entire mountain ranges bear visible evidence of these frozen processes operating across thousands of years. One of the clearest signs of glacial erosion is the formation of deep, wide valleys with steep sides. Rivers alone usually carve narrow V-shaped valleys because flowing water concentrates most of its erosion near the bottom of the channel. Glaciers behave differently because they fill much larger portions of the valley with thick, moving ice. Instead of cutting only downward, glaciers grind against both the valley floor and surrounding walls simultaneously. Over time, the valley becomes wider, deeper, and more rounded in shape. Many famous landscapes around the world were transformed through this gradual widening process. Places such as Yosemite Valley in California, the fjords of Norway, and parts of New Zealand display enormous valleys carved by glaciers long ago. Today, these landscapes attract millions of visitors who admire their towering cliffs, broad valley floors, and dramatic scenery. Yet the shapes people admire today are often the result of glaciers slowly reshaping the terrain across ages through erosion and movement. Fjords provide one of the most striking examples of glacial transformation. These long, narrow sea inlets, surrounded by steep cliffs, originally formed when glaciers carved deep valleys below sea level. After the glaciers retreated, ocean water flooded into the empty valleys, creating the fjords seen today in places like Norway, Greenland, and parts of Alaska. The towering walls rising beside the water reveal the enormous erosive power glaciers once held in these regions. Glacial erosion can also create isolated peaks and sharp ridges within mountain ranges. As glaciers carve away rock from multiple sides of a mountain, steep pointed summits may gradually emerge. Some famous alpine peaks owe part of their dramatic appearance to glaciers eroding the surrounding terrain over time. The landscape becomes sculpted not through sudden events, but through countless years of pressure, freezing, scraping, and slow movement. Even after glaciers retreat, the terrain they transformed continues preserving evidence of their former presence. Wide valleys, polished rock surfaces, hanging valleys, steep cliffs, and scattered boulders all remain behind as records of ancient ice movement. In some regions, forests now cover landscapes once buried beneath thick glaciers during past ice ages. Rivers may flow through valleys, originally carved by ice, long before human civilization existed in those regions. Some scientists describe glaciers as architects of the landscape because of the lasting marks they leave behind. Mountains become sharper in some places and smoother in others. Valleys widen and deepen. Cliffs rise higher above newly carved floors. Lakes form where glaciers once rested. The terrain itself carries the memory of the glacier long after the ice disappears. Every scraped rock surface and widened valley tells part of the hidden history of moving ice. One of the easiest ways to recognize the influence of ancient glaciers is by looking at the shape of a valley. Landscapes shaped by glaciers often appear very different from those carved mainly by rivers. A river usually cuts downward into the land over time, creating a narrow valley with sloping sides that form a rough V shape. Glaciers reshape valleys in a much broader and deeper way, because the ice fills the entire valley from side to side as it moves. Instead of eroding only a narrow channel near the center, the glacier grinds against the valley floor and walls simultaneously. Over thousands of years, this process transforms the valley into a much wider formation with steep sides and a broad, flat floor. These glacial formations are known as U-shaped valleys because of their rounded appearance when viewed from a distance or from above. The difference between river-carved valleys and glacier-carved valleys becomes especially noticeable in mountainous regions where both types of erosion may exist side by side. River valleys tend to appear narrow and sharply angled, while glacial valleys often look far larger, smoother, and more open. The floor of a U-shaped valley may stretch broadly between steep cliffs, rising high above on either side. Many famous mountain landscapes owe their dramatic appearance to this slow shaping process, carried out by moving glaciers across ages. Yosemite Valley in California is one of the best-known examples of a glacier-carved valley. Towering granite cliffs rise sharply above a broad valley floor, shaped by ancient glaciers that once filled the region with thick moving ice. The valley appears far wider and steeper than most river valleys, because glaciers carve not only downward, but outward against the surrounding rock walls. Similar U-shaped valleys exist throughout the Alps, the Himalayas, Patagonia, New Zealand, and parts of Scandinavia, where glaciers once dominated the landscape. The enormous size of glaciers allows them to reshape terrain in ways rivers alone cannot easily achieve. A river flows primarily through a narrow channel, concentrating erosion near the bottom of the valley. A glacier may fill the entire valley with ice hundreds or even thousands of feet thick. As the glacier moves, embedded rocks scrape continuously against both the valley floor and walls. Plucking removes additional rock from fractured surfaces. The combined effect slowly widens the valley, while also deepening it over time. Some glacial valleys contain features known as hanging valleys. These form when smaller tributary glaciers join larger main glaciers flowing through deeper valleys below. Because the larger glacier erodes more powerfully, the main valley often becomes much deeper than the smaller side valleys connected to it. After the glacier's retreat, rivers flowing through the smaller hanging valleys may spill dramatically over cliffs into the larger valley below, creating waterfalls. Many famous waterfalls in glacier-shaped regions exist because of this difference in erosion depth between connected glaciers. The steep cliffs found within U-shaped valleys can create dramatic scenery that feels almost overwhelming in scale. In some regions, the walls rise thousands of feet above the valley floor, with nearly vertical faces of exposed rock. These cliffs often formed because glaciers carved deeply into the valley while removing much surrounding material. The sheer weight and movement of the ice gradually sharpened the contrast between the broad valley floor and the towering rock walls above. Glacier-carved valleys also tend to contain smoother surfaces compared with many river valleys. Abrasion beneath the glacier polishes exposed rock and removes rough irregularities over time. Rounded hills and curved slopes may remain long after the glacier disappears. In some areas, polished bedrock still displays visible grooves and scratches left behind by rocks embedded in the moving ice thousands of years earlier. These marks preserve the direction and movement of glaciers that once occupied the valley. The broad shape of glacial valleys can strongly influence modern ecosystems and human settlement patterns. Wide valley floors often create space for rivers, forests, farms, towns, and transportation routes. In many mountainous regions, roads and railways now follow paths originally carved by ancient glaciers because the valleys provide easier travel through otherwise rugged terrain. Lakes formed by glacial erosion also supply water for communities and support wildlife across many parts of the world. In colder coastal regions, some U-shaped valleys later became flooded by rising sea levels after glaciers melted away. These flooded valleys formed fjords, where steep cliffs rise directly from deep ocean water. Norway contains some of the most famous fjords on Earth, though similar formations also exist in Greenland, Alaska, Canada, Chile, and New Zealand. The incredible depth and steepness of fjords reveal just how powerfully glaciers once carved through these landscapes before retreating. Even in regions where glaciers disappeared thousands of years ago, the valleys they shaped continue dominating the landscape today. Forests may cover the slopes. Rivers may flow quietly across the valley floor. Cities and roads may occupy areas once buried beneath thick ice. Yet the land itself still preserves the hidden influence of glaciers that slowly carved these enormous formations through patience, pressure, movement, and time. Long after glaciers disappear, the landscapes they shaped continue preserving clear evidence of their former presence. Mountains, valleys, lakes, ridges, and exposed rock surfaces often contain visible clues showing how ancient ice once moved across the region. In many places, people travel through glacier-shaped landscapes every day without realizing that the terrain itself acts almost like a historical record carved directly into the earth. The marks left behind by glaciers can survive for thousands of years, allowing scientists to study ice movement from distant ages long after the glaciers themselves have melted away. One of the reasons glacial landscapes remain so recognizable is because glaciers reshape terrain on such a large scale. Rivers may slowly shift channels over time, or alter local sections of a valley, but glaciers can transform regions at once. Massive ice sheets that once covered parts of North America and northern Europe left behind broad plains, rolling hills, deep lakes, and polished rock surfaces stretching across enormous distances. Even today, the shape of many modern landscapes still reflects the movement of glaciers that vanished near the end of the last major ice age. Exposed bedrock often provides some of the clearest evidence of past glacier activity. As glaciers moved across the land, rocks trapped beneath the ice scraped grooves and scratches into the surface below. These markings, known as striations, can remain preserved for very long periods if later erosion does not remove them. Scientists examine the direction of these scratches to understand how glaciers once flowed across a region. In some places, entire rock surfaces appear smoothed and polished by ancient ice movement, almost as though the landscape had been sanded down over thousands of years. Large boulders sitting in unusual locations also reveal evidence of past glaciers. Some rocks carried within glaciers were eventually deposited far from their original source after the ice melted away. These transported stones, called glacial erratics, may rest in landscapes where the surrounding rock type is different. A massive granite boulder might sit alone within a region composed mainly of limestone because a glacier carried it there from distant mountains long ago. These misplaced rocks act almost like footprints left behind by the glacier's journey across the land. Many lakes found across northern regions owe their existence to glaciers as well. As glaciers advanced and retreated, they carved depressions into the ground that later filled with water after the ice melted. Some lakes formed where chunks of ice became buried beneath sediment before slowly melting away, leaving rounded basins behind. Others occupy valleys deepened by glacial erosion over thousands of years. In places such as Canada, Finland, Scotland, and parts of the northern United States, entire networks of lakes exist because of ancient glacial activity. Rolling hills and ridges created from glacial deposits also preserve records of former ice movement. As glaciers melted, they released huge amounts of rock, sand, gravel, and sediment that had been carried within the ice. This material accumulated into long ridges, mounds, and plains across the land. Some ridges mark the former edges of glaciers, where melting and deposition occurred for extended periods. These formations allow scientists to estimate where glaciers once stood and how far they extended during colder climatic periods. The terrain shaped by glaciers often influences modern rivers, forests, and ecosystems. Rivers may follow paths first carved by ice long ago. Wetlands may form in low areas left behind by retreating glaciers. Fertile soils produced from glacial sediment can support agriculture and forests across large regions. In many ways, glaciers continue influencing modern landscapes even after disappearing, because the terrain they created shapes how water, plants, animals, and people interact with the environment. Scientists studying ancient glaciers often combine evidence from many landforms to reconstruct past climates. Smooth rock surfaces, glacial valleys, erratic boulders, sediment ridges, and lake basins all provide pieces of a larger environmental history. By examining these features together, researchers can estimate how glaciers expanded and retreated over time. The landscape itself becomes a kind of natural archive, preserving evidence of colder periods in Earth's past. Some of the strongest evidence for ancient ice sheets comes from regions where glaciers no longer exist at all. Parts of the central United States, northern Germany, Poland, and southern England were once buried beneath thick ice during past glacial periods. Although the glaciers vanished thousands of years ago, the terrain still reveals their influence through scattered boulders, broad plains, and patterns of glacial sediment. The land continues carrying the memory of frozen landscapes that existed long before recorded human history. In mountainous regions, glacier-shaped terrain often creates some of the most visually dramatic scenery on Earth. Sharp ridges, steep valleys, hanging waterfalls, and polished cliffs all reflect the powerful erosion glaciers once carried out. Visitors admiring these landscapes today are often looking at terrain slowly sculpted by moving ice over immense stretches of time. What appears permanent and timeless was actually shaped through continuous movement, pressure, freezing, melting, and erosion unfolding gradually across thousands of years. As glaciers move across the land, they carry more than frozen water alone. Embedded within the ice are rocks, gravel, sand, and countless smaller particles gathered from mountains, valleys, and exposed ground along the glacier's path. Some of this material rests on the glacier surface after falling from nearby cliffs, while other pieces become trapped deep inside the ice or frozen along the glacier's base. Over time, glaciers transport enormous amounts of material across great distances, acting almost like slow-moving conveyor belts, reshaping Earth's surface. The scale of this transportation can be extraordinary. A glacier may carry rocks weighing many tons for miles across valleys and plains before finally depositing them elsewhere after the ice melts away. Smaller particles travel alongside larger boulders within the moving ice. Entire landscapes may gradually receive layers of sediment carried from distant mountains over thousands of years. In some regions, glaciers transported material across areas larger than modern countries during past ice ages, when enormous ice sheets covered vast portions of the planet. Material carried by glaciers is known collectively as glacial sediment. Unlike rivers, which often sort sediment by size as water flows downstream, glaciers transport many sizes of material together within the ice. Fine clay, sand, gravel, and giant boulders may all travel side by side inside the glacier. This mixture reflects the immense strength of moving ice. A river might struggle to move very large rocks, except during floods, but a glacier can slowly carry massive stone blocks embedded within its frozen body for long periods. Some sediment becomes trapped at the bottom of the glacier, where it scrapes against the ground during movement. Other material remains frozen within deeper layers of the ice itself. Rocks falling onto the glacier surface from nearby mountain slopes may slowly sink downward as fresh snowfall buries them each year. Over centuries, the glacier continuously collects, transports, and redistributes material across the land while moving under the force of gravity. When glaciers eventually melt or retreat, the sediment they carried becomes deposited across the land. This process creates many new landforms composed of glacial debris. The material released from melting glaciers often remains scattered in uneven mixtures because the glacier transported many particle sizes together. Some areas become covered in smooth plains of sediment, while others contain ridges, hills, or isolated boulders left behind after the ice disappears. One of the most common glacial deposits is called till. Till consists of unsorted sediment deposited directly by melting ice. Unlike river sediment, which is often layered and organized by flowing water, till appears jumbled together with particles of many sizes mixed throughout. A single deposit may contain fine clay beside large stones and gravel, because the glacier transported everything together without separating the material by size or weight. Large ridges formed from glacial deposits are known as moraines. These ridges often mark places where glaciers paused for long periods, while melting and depositing debris along their edges. Moraines can form beside glaciers, beneath them, or at their farthest points of advance. Some moraines stretch across valleys like natural walls, built slowly from rock and sediment released by the retreating ice. Scientists often study these ridges to understand where glaciers once extended during colder periods in Earth's history. In many regions, glacial deposits strongly influence modern landscapes and ecosystems. Fertile farmland across parts of North America and Europe exists because glaciers left behind rich sediment during ancient ice ages. Rivers may flow around ridges of deposited material. Forests may grow upon soils formed from glacial debris. Lakes can develop where sediment blocks drainage pathways or where melting ice leaves depressions behind in the terrain. Some of the most striking glacial deposits are isolated erratic boulders, resting far from their original source. These massive stones may appear completely out of place within the surrounding landscape because glaciers carried them there from distant mountains long ago. In some regions, people once believed such boulders must have been moved by floods, giants, or other extraordinary forces, because the true explanation involving ancient glaciers was not yet understood. Meltwater flowing from glaciers also plays an important role in redistributing sediment after the ice begins melting. Streams emerging from glaciers often carry huge amounts of sand and fine rock particles downstream. Broad plains known as outwash plains can form where meltwater spreads sediment across large areas beyond the glacier's edge. Braided rivers with constantly shifting channels often develop in these regions because the water carries so much loose glacial material. During major ice ages, glaciers transformed not only mountains and valleys, but entire continental landscapes through transport and deposition. Massive ice sheets repeatedly advanced and retreated across northern regions, carrying sediment with them as they moved. The modern terrain of many countries still reflects these ancient cycles of glacial transport. Rolling hills, scattered lakes, fertile plains, and unusual rock distributions all preserve evidence of material once carried within enormous moving ice sheets thousands of years ago. Their quiet movement can hide the scale of this transport. A glacier may only advance a small distance within a single day, yet over centuries, it can move entire mountainsides of debris across vast regions. Every rock trapped within the ice becomes part of the glacier's slow journey through the land. Then, when melting finally releases that material back onto the earth, entirely new landforms emerge from the deposits left behind. As glaciers deposit sediment across the land, entirely new landforms gradually emerge from the material left behind. Ridges, rolling hills, plains, and broad fields of gravel may all develop through the slow accumulation of glacial debris. These features often appear so natural within modern landscapes that it can be difficult to imagine they were created by moving ice long ago. Yet in many regions, The land itself still reflects the gradual build-up and redistribution of material carried by glaciers over thousands of years. One of the most noticeable effects of glacial deposition is the formation of ridges known as moraines. These ridges develop where glaciers deposit rock, gravel, and sediment along their edges, or at the point where the glacier temporarily stops advancing. Over time, the debris accumulates into long, uneven walls, stretching across valleys or open plains. Some moraines remain relatively small, while others rise prominently across the land and can extend for many miles. In regions once covered by vast ice sheets, chains of moraines still mark the former boundaries reached by glaciers during colder climatic periods. Broad plains formed from glacial sediment also appear across many parts of the world. As glaciers melt, enormous amounts of loose material are released from the ice. Meltwater streams carry much of this sediment outward and spread it across nearby lowlands. Over time, these deposits build wide, flat areas composed of sand, gravel, and fine particles crushed beneath the glacier. Some of the fertile agricultural land found today in northern Europe and North America exists because glaciers slowly deposited rich sediment across the region during past ice ages. Sediment released by glaciers continues changing the landscape long after the ice itself retreats. Wind may carry fine particles across open plains. Rivers flowing through glacial deposits may reshape valleys and create new channels over time. Lakes may form behind ridges of deposited material, or within depressions left behind by melting ice blocks. In many regions, the surface layers of the Earth consist largely of material transported and deposited by glaciers during ancient periods of extensive glaciation. The movement of glaciers redistributes material on an enormous scale. Rocks originally formed within mountain ranges may eventually become scattered across distant plains hundreds of miles away. Fine rock flour created through abrasion beneath glaciers may settle into lakes and river systems far downstream. Entire hills and ridges composed of glacial debris reveal how thoroughly glaciers can reorganize the surface layers of the landscape through slow movement and deposition. Some glacial landforms possess unusual shapes that clearly reveal the direction of past ice movement. Long, smooth hills known as drumlins often form beneath moving glaciers as sediment becomes molded by the pressure and flow of the ice above. Drumlins usually appear stretched in the direction the glacier once traveled, almost like fingerprints left behind across the land. In places such as Ireland, Canada, and parts of the northern United States, fields of drumlins still preserve visible patterns created by glaciers thousands of years ago. Another remarkable feature formed by glacial deposition is the esker. Eskers are long winding ridges made from sand and gravel, deposited by rivers flowing beneath glaciers. As meltwater streams traveled through tunnels inside or beneath the ice, they carried sediment along their channels. When the glacier eventually melted away, the sediment remained behind as narrow ridges tracing the former paths of hidden glacial rivers. Some eskers stretch across the land for many miles, like raised natural roadways, winding through forests and plains. Kettle lakes provide another example of how glacial deposits shape geography. During glacier retreat, large blocks of ice sometimes broke away and became buried beneath loose sediment. As these isolated ice blocks slowly melted, the ground above collapsed inward, leaving depressions that later filled with water. Thousands of small lakes across formerly glaciated regions formed through this process. In some areas, entire chains of lakes mark places where melting ice once remained buried beneath glacial sediment long after the main glacier had disappeared. The influence of glacial transport becomes especially clear when viewing large regions from above. Satellite images reveal sweeping patterns of ridges, lakes, plains, and rolling terrain left behind by former ice sheets. What may appear random from ground level often forms organized structures created through glacier movement and deposition across immense distances. Entire landscapes preserve the memory of how glaciers once advanced, transported sediment, and slowly retreated again. In some places, cities and towns now stand directly upon glacial deposits without most people realizing it. Roads cross ancient moraines. Farms occupy fertile plains formed from glacier sediment. Lakes used for recreation and drinking water fill depressions created by melting ice thousands of years ago. The hidden influence of glaciers remains deeply connected to the modern geography of many parts of the world. There have been periods in Earth's history when glaciers expanded beyond the mountain valleys and polar regions where most glaciers exist today. During these colder eras, enormous ice sheets spread outward across continents, covering vast areas of land beneath thick layers of ice. Scientists refer to these periods as ice ages or glacial periods. During the height of an ice age, landscapes that are now forests, farmland, cities, and coastlines may have been buried beneath moving ice thousands of feet thick. The scale of these frozen worlds is difficult to imagine because modern glaciers represent only a small remnant of the much larger ice systems that once dominated huge portions of the planet. An ice age does not mean the entire Earth becomes frozen solid. Even during the coldest glacial periods, many tropical and equatorial regions remained free from permanent ice. Instead, ice ages involve long-term shifts in climate that allow glaciers and ice sheets to expand across much larger areas than normal. Temperatures decrease gradually over extended periods, snowfall accumulates faster than melting occurs, and glaciers slowly grow each year. Over thousands of years, small changes in climate can eventually produce enormous expansions of ice across continents. The most recent major ice age reached its greatest extent roughly 20,000 years ago. At that time, large portions of North America, Northern Europe, and Asia were covered beneath massive ice sheets. In North America, ice stretched southward across much of Canada and into parts of the northern United States. Similar ice sheets spread across Scandinavia, the British Isles, and northern regions of Europe. Sea levels during this period were much lower because enormous amounts of water remained locked within glaciers and continental ice sheets rather than existing in the oceans. The thickness of these ancient ice sheets was extraordinary. In some places, the ice reached thicknesses greater than modern skyscrapers are tall. Entire mountain ranges disappeared beneath the frozen surface. The pressure exerted by the weight of the ice became so immense that parts of the Earth's crust were slowly pushed downward beneath it. Even today, some northern regions continue slowly rising upward after the disappearance of these ancient ice sheets because the land is still adjusting to the loss of so much weight. The growth of ice sheets during glacial periods depended upon long-term climatic conditions remaining cold enough to preserve snowfall each year. Winters alone were not sufficient. Snow that accumulated during colder months also needed to survive through warmer seasons without fully melting away. Over many centuries, this gradual imbalance allowed glaciers to expand farther outward from mountain regions and polar areas. Small changes repeated consistently over time eventually transformed the landscape on continental scales. Scientists believe several different natural factors contribute to the beginning and ending of ice ages. Variations in Earth's orbit around the Sun can slightly alter the amount of solar energy reaching different parts of the planet over extremely long timescales. Changes in ocean circulation, atmospheric composition, volcanic activity, and continental arrangement may also influence long-term climate patterns. None of these changes produce immediate effects on human timescales, but across thousands of years, they can gradually shift global temperatures enough to support expanding or retreating ice sheets. During major glacial periods, the environment across many regions looked very different from today. Vast frozen plains extended across northern continents. Strong winds carried fine glacial sediment across open landscapes. Large mammals such as woolly mammoths, steppe bison, and woolly rhinoceroses inhabited cold grasslands bordering the ice sheets. Human populations living during these periods adapted to colder climates while migrating across landscapes shaped by advancing and retreating glaciers. As glaciers expanded, they transformed rivers, forests, coastlines, and ecosystems. Massive amounts of water became trapped inside growing ice sheets, causing global sea levels to fall. Land bridges that are now submerged beneath the ocean emerged between continents and islands. One famous example is the Bering Land Bridge, which once connected Asia and North America during periods of lower sea level. Scientists believe early human populations migrated across this land bridge thousands of years ago, while glaciers covered much of the surrounding northern landscape. The advance of ice sheets also reshaped weather patterns across the planet. Cold air flowing from large glacial regions influenced storms, rainfall, and atmospheric circulation beyond the edges of the ice itself. Deserts expanded in some areas, while wetter conditions developed elsewhere. Entire ecosystems shifted gradually in response to changing temperatures and precipitation patterns associated with the expanding ice. Although ice ages are often associated with extreme cold, the changes usually unfolded gradually rather than suddenly. A glacier advancing across a region might take centuries to noticeably alter the local landscape. Forests slowly retreated. Rivers changed course. Snow accumulated more consistently each year. The planet transitioned between colder and warmer periods through processes operating across ages rather than through rapid transformation. Eventually, warmer climatic conditions caused the great ice sheets to retreat once again. Temperatures slowly increased, melting exceeded snowfall accumulation, and the glaciers gradually shrank back toward polar and mountain regions. Yet the marks left behind by these ancient ice sheets remain deeply etched into the landscape. Lakes, valleys, ridges, plains, and glacial deposits across much of the modern world still preserve evidence of those colder ages when vast frozen sheets covered enormous portions of the Earth. The idea of continents buried beneath moving ice may seem almost unimaginable today, especially in regions now filled with forests, farms, highways, and cities. Yet the terrain itself still carries the memory of those ancient frozen worlds. Every glacial valley, polished rock surface, scattered erratic boulder, and rolling moraine, reflects a time when ice slowly expanded across the land under colder skies during the long climatic cycles of Earth's history. One of the most important things scientists have learned about Earth's climate is that it does not remain completely stable over time. Instead, the planet moves through repeating cycles of colder and warmer conditions that unfold across thousands of years. During colder periods, glaciers and ice sheets expand outward across the land. During warmer periods, much of that ice gradually melts and retreats. These slow climatic shifts have repeated many times throughout Earth's history, shaping landscapes, oceans, ecosystems, and even the movement of human populations across ages. The changes involved in these climate cycles happen more slowly than ordinary seasonal changes. A cold winter or warm summer does not create an ice age. Instead, glacial cycles develop gradually through countless generations as temperatures shift little by little over thousands of years. Snowfall accumulates more consistently in colder periods, glaciers begin expanding, and ice sheets slowly spread across larger areas. During warmer phases, melting increases, glaciers retreat, and landscapes once buried beneath ice become exposed again. Scientists studying these long-term climate patterns often compare Earth's climate system to a giant set of interconnected balances. Oceans store and move heat around the planet. Ice reflects sunlight back into space. Atmospheric gases influence how much warmth remains trapped near the surface. Changes in one part of the system can gradually influence conditions elsewhere. Over long timescales, even relatively small shifts can eventually produce major changes in glacier size and global climate patterns. One of the key drivers behind these repeating glacial cycles involves subtle variations in Earth's orbit and orientation as it travels around the Sun. The shape of Earth's orbit changes slightly over very long periods. The angle of the planet's tilt also shifts gradually, and the direction of Earth's axis slowly changes through a motion called precession. These variations alter how sunlight is distributed across different parts of the planet during different seasons. The effects are small on yearly timescales, but become significant when accumulated across many thousands of years. When cooler summers allow snow to survive more easily in polar and mountain regions, glaciers may begin expanding gradually over time. As ice coverage increases, even more sunlight reflects back into space, because bright ice surfaces absorb less heat than darker land or ocean water. This reflective effect can further support cooling and glacier growth. During warmer periods, shrinking ice exposes darker surfaces that absorb more heat, contributing to additional warming and glacier retreat. These feedback processes help amplify long-term climate changes already underway. Ice cores extracted from glaciers and polar ice sheets provide some of the clearest evidence for these repeating climate cycles. Deep within the ice, layers preserve records of snowfall, atmospheric gases, volcanic ash, and conditions stretching back hundreds of thousands of years. By studying these layers, scientists can reconstruct past temperatures and identify periods when glaciers expanded or retreated. The ice reveals that Earth has repeatedly shifted between colder glacial periods and warmer interglacial periods through recent geological history. Human civilization developed during one of these warmer interglacial periods after the retreat of the last major ice sheets. Roughly 12,000 years ago, temperatures gradually increased enough for glaciers to retreat across large areas of the northern hemisphere. Forests spread into newly exposed regions, sea levels rose as melting ice returned water to the oceans, and many landscapes slowly transformed into the environments familiar today. Agriculture, permanent settlements, and eventually large civilizations emerged during this relatively stable, warmer period. The transition between glacial and warmer periods can dramatically reshape the planet over time. Expanding ice sheets lower sea levels by trapping water on land, while retreating glaciers raise sea levels as melting ice returns to the oceans. Coastlines shift, rivers change course, ecosystems move gradually northward or southward depending on climate conditions. Animal populations adapt, migrate, or disappear as conditions evolve over thousands of years. Evidence of these repeating cycles exists across landscapes all over the world. Ancient shorelines reveal periods when sea levels were much lower during glacial ages. Layers of sediment preserve records of colder and warmer climates. Fossils show how plants and animals changed distribution as temperatures shifted. Glacial landforms mark regions once buried beneath ice before later warming exposed them again. Together, these records reveal that Earth's climate has always been dynamic rather than fixed. Glacial cycles unfold across spans far longer than recorded human history. Entire civilizations rise and disappear within only a small fraction of a glacial cycle. Mountains may slowly erode, while glaciers advance and retreat repeatedly across surrounding valleys. Forests spread across landscapes once buried beneath ice, only for future cooling periods to eventually allow glaciers to return once again. Although the exact timing and intensity of future climate changes remain subjects of scientific study, the geological record clearly shows that Earth's climate system has experienced repeated shifts between colder and warmer states throughout its history. Glaciers expand, ice retreats, sea levels rise and fall. Landscapes change gradually under the influence of these long repeating cycles operating across ages. Deep inside a glacier, the ice is arranged in layers that slowly accumulated over years through repeated snowfall. Each winter adds a fresh covering of snow across the glacier surface. Over time, newer snow buries older layers beneath increasing weight and pressure. As the snow compresses into ice, the original layers often remain preserved within the glacier, like pages stacked within an enormous frozen archive. Scientists studying glaciers can examine these layers to learn about conditions stretching far back into the past. In many ways, glacier layers resemble the growth rings inside a tree trunk. A tree forms new rings each year as it grows, and each ring preserves evidence about conditions during that season. Glaciers record time in a somewhat similar way. Every layer of snow that survives long enough to become compacted into ice represents a particular period of accumulation. Some layers may reflect years of heavy snowfall, while others reveal drier or windier conditions. Together, the stacked layers preserve a long chronological record, extending deep beneath the glacier surface. The uppermost layers of a glacier are always the youngest, because they formed from the most recent snowfall. Deeper layers are progressively older, because they were buried earlier beneath centuries of additional accumulation. In large ice sheets, such as those covering Greenland and Antarctica, the deepest ice may preserve snowfall that originally fell hundreds of thousands of years ago. The farther scientists travel downward through the glacier, The farther back in time, they are effectively observing Earth's environmental history. As layers become buried deeper beneath the surface, pressure gradually compresses the ice more tightly together. Air spaces shrink, crystals deform, and the ice becomes denser with depth. In some glaciers, the deepest layers are squeezed so tightly that the original snowfall patterns become distorted under immense pressure from the overlying ice. Yet despite this compression, many ancient layers remain remarkably well preserved. Scientists can often still identify yearly accumulation patterns even deep within thick polar ice sheets. One of the reasons glaciers are so valuable to scientists is because they preserve tiny particles from the atmosphere trapped within the ice. Dust carried by ancient winds may settle onto the glacier surface before becoming buried beneath later snowfall. Ash from volcanic eruptions can spread through the atmosphere and settle across glaciers thousands of miles away. Sea salt, pollen, smoke particles, and industrial pollutants may also become trapped within accumulating snow layers. Once buried and frozen inside the glacier, these particles can remain preserved for extremely long periods. By studying the composition of different ice layers, scientists can reconstruct details about past climates and conditions. Layers containing much dust may reflect colder and drier conditions when strong winds carried more sediment through the atmosphere. Volcanic ash layers help researchers identify major eruptions from distant periods of history. Traces of pollen preserved in the ice may reveal what kinds of vegetation existed in nearby regions when the snow originally fell. The annual layering within glaciers is sometimes visible directly to the eye. In exposed sections of ice, alternating bands may appear slightly lighter or darker, depending on seasonal differences in snowfall and sediment content. Summer snow can differ from winter snow because warmer conditions may produce slight melting or changes in particle accumulation. Over long periods, these subtle differences build visible patterns within the glacier, preserving a frozen sequence of environmental changes through time. Scientists extract long cylindrical sections of glacier ice called ice cores to study these preserved layers in detail. Ice cores may extend thousands of feet deep through glaciers and polar ice sheets. Each section of the core contains information about the period when that layer originally formed. By carefully analyzing the ice, researchers can estimate temperature patterns, atmospheric conditions, volcanic activity, and even large-scale climate changes stretching far into the past. The deeper scientists drill into a glacier, the more ancient the preserved record becomes. Some Antarctic ice cores contain ice formed hundreds of thousands of years ago during climates very different from today. These deep layers allow scientists to study multiple glacial cycles preserved within the ice itself. In effect, glaciers provide one of the longest continuous environmental records available anywhere on Earth. The preservation within glaciers can be so effective that traces of ancient events remain detectable after enormous spans of time. Ash from volcanic eruptions, changes in atmospheric chemistry, and shifts in global climate all become locked into the ice as snowfall accumulates layer by layer. In some rare cases, glaciers have even preserved ancient plants, insects, and human artifacts trapped within the frozen environment long after they disappeared elsewhere. The deeper scientists study glacier ice, the more clearly they begin to understand that glaciers preserve more than frozen water alone. Tiny particles trapped inside the layers of ice provide detailed clues about the atmosphere and environment from distant periods in Earth's history. Dust carried by ancient winds, ash from volcanic eruptions, sea salt from ocean storms, smoke from large fires, and microscopic particles from plants all become preserved within accumulating snowfall. Once buried beneath later layers and compressed into ice, these materials can remain sealed inside the glacier for ages. Among the most valuable materials preserved within glacier ice are tiny pockets of ancient gases trapped between ice crystals. As snowfall compresses into dense ice, small bubbles of air become sealed inside the glacier. These bubbles preserve samples of the atmosphere exactly as it existed when the snow originally fell. Scientists can analyze these ancient air pockets to measure how atmospheric conditions changed over hundreds of thousands of years. In many ways, glaciers act like frozen containers, storing pieces of Earth's ancient atmosphere deep within the ice. Dust preserved inside glaciers provides important information about conditions during different climatic periods. Colder and drier climates often produce stronger winds capable of carrying greater amounts of fine sediment through the atmosphere. When this dust settles onto glaciers, it becomes trapped within the accumulating layers. Scientists examining dust concentrations inside ice cores can identify periods when deserts expanded, storms intensified, or conditions shifted across large regions of the planet. Volcanic eruptions also leave clear signatures inside glacier ice. Large eruptions can inject ash and sulfur particles high into the atmosphere where winds spread them across enormous distances. Some volcanic particles eventually settle onto glaciers and become preserved within the snow layers. Scientists studying these volcanic deposits can identify major eruptions that occurred thousands of years ago, even when written historical records do not exist. In some cases, ice cores preserve evidence of eruptions far older than human civilization itself. The chemical composition of glacier ice can reveal changes in temperature as well. Different forms of oxygen and hydrogen isotopes become incorporated into snowfall under different climatic conditions. By measuring the ratios of these isotopes within ice layers, scientists can estimate past temperatures during the time the snow originally formed. This method allows researchers to reconstruct climate patterns stretching beyond recorded human history. One of the remarkable aspects of glacier research is the level of detail preserved within the ice. In some cases, scientists can identify individual years within ice core records, much like counting tree rings. Seasonal changes in dust, chemistry, and snowfall create repeating patterns within the layers. These patterns allow researchers to establish long chronological timelines, showing how conditions shifted gradually through time. Some Antarctic ice cores preserve climate records older than many mountain ranges in their present form. Deep beneath the polar surface, ancient snowfall from distant ages remains trapped exactly where it accumulated long ago. Each layer stores information about the environment during the period when that snow originally fell. Together, the layers form one of the most complete long-term environmental records found anywhere on Earth. Glacier ice also preserves evidence of more recent human influence upon the atmosphere. Industrial pollutants released during the modern era have become detectable within upper ice layers formed during recent centuries. Scientists can observe changes in atmospheric chemistry associated with industrialization by comparing newer layers with much older ice formed before large-scale human industry existed. The glacier quietly records these changes each year as fresh snowfall settles across the surface. Glaciers also preserve tiny samples of ancient air inside countless microscopic bubbles. As fresh snowfall accumulates and slowly compresses into dense glacier ice, small pockets of the surrounding atmosphere become sealed between the ice crystals. These bubbles remain trapped deep within the glacier for thousands or even hundreds of thousands of years. In effect, glaciers preserve actual pieces of Earth's ancient atmosphere frozen in place beneath the surface. When scientists first realized these bubbles contained ancient air, glaciers became even more valuable as records of climate history. Before this discovery, researchers could study layers of dust and sediment trapped in the ice, but the preserved air bubbles provided something more direct. They offered the possibility of measuring the atmosphere itself as it existed during distant periods of Earth's history. Each bubble acts almost like a tiny time capsule sealed naturally inside the glacier. The deeper the ice layer, the older the trapped air tends to be. Near the glacier surface, the bubbles contain relatively modern air because the snow formed recently. Far below, the bubbles preserve atmospheric samples from ages long before human civilization existed. In the deepest Antarctic ice cores, some trapped air dates back hundreds of thousands of years. Scientists can carefully extract and analyze these bubbles to study how Earth's atmosphere changed across repeated glacial cycles. Inside the bubbles are gases such as oxygen, nitrogen, methane, and carbon dioxide. By measuring the concentration of these gases within ancient air samples, scientists can reconstruct past atmospheric conditions with remarkable accuracy. Changes in carbon dioxide and methane levels often correspond closely with major climate shifts recorded elsewhere in the ice. During colder glacial periods, greenhouse gas concentrations tended to be lower. During warmer periods, concentrations increased again as climate conditions changed. The process of analyzing ancient air trapped inside glacier ice requires extraordinary precision. Scientists cut carefully prepared sections from deep ice cores inside extremely clean laboratory environments to avoid contamination from modern air. The ice may then be crushed or melted within sealed containers, so the trapped gases can be collected and measured. Sophisticated instruments detect even tiny variations in gas composition preserved inside the bubbles. The results of these measurements have transformed scientific understanding of Earth's climate system. By comparing ancient greenhouse gas levels with temperature records preserved in the same ice layers, researchers discovered strong connections between atmospheric composition and long-term climate change. The ice revealed that Earth's atmosphere has changed repeatedly throughout history, alongside the advance and retreat of glaciers and ice sheets. Methane preserved within ice bubbles can also reveal changes in wetlands, vegetation, and biological activity across ancient climates. Dust levels may indicate drier conditions and stronger winds during colder periods. Sulfur compounds may reflect volcanic eruptions. Together, the gases and particles preserved inside glaciers provide a deeply detailed picture of conditions stretching back through deep time. Scientists studying these ancient air bubbles have also learned how rapidly some climate transitions unfolded in the past. Certain ice core records reveal periods where temperatures and atmospheric conditions shifted surprisingly quickly on geological timescales. Although these changes still unfolded across many human generations, the ice shows that Earth's climate system can respond strongly once certain environmental thresholds are crossed. The preservation inside glaciers is so effective because the deep ice remains isolated from the outside environment once fully compacted. The trapped air bubbles become sealed away beneath enormous pressure and low temperatures that slow chemical changes over time. In many ways, glaciers provide one of the most reliable long-term storage systems found anywhere in nature. The ancient atmosphere remains protected inside the ice until scientists eventually recover it through drilling and analysis. The study of ancient glacier air has also revealed how closely connected Earth's systems truly are. Atmospheric composition influences temperature. Temperature affects glacier growth and melting. Expanding ice sheets alter sea levels, weather patterns, and ecosystems across the planet. The air bubbles trapped inside glaciers preserve evidence of these interconnected processes unfolding repeatedly across hundreds of thousands of years. To study the hidden history preserved inside glaciers, scientists rely upon one of the most important tools in climate research, known as the ice core. An ice core is a long cylindrical section of ice carefully drilled and removed from a glacier or ice sheet. These frozen columns may extend hundreds or even thousands of feet deep beneath the surface. Each layer within the core represents snowfall that accumulated during a different period in Earth's history. By examining the ice layer by layer, scientists can reconstruct detailed records of ancient climates, atmospheric conditions, volcanic eruptions, and environmental changes stretching far into the past. The process of collecting an ice core often takes place in some of the coldest and most remote environments on Earth. Research teams may spend weeks or months working in Antarctica, Greenland, or isolated mountain glaciers surrounded by snow and ice in every direction. Powerful drilling systems slowly cut through the glacier while preserving the delicate layers inside the core. Each extracted section is carefully labeled, stored at freezing temperatures, and transported to laboratories where scientists begin the long process of analysis. Some ice core projects have required many years of preparation because drilling deep into thick polar ice sheets presents enormous technical challenges. In Antarctica, researchers have extracted ice cores extending more than 2 miles beneath the surface. The deepest sections contain ice formed hundreds of thousands of years ago during climates very different from today. Every foot of depth represents another journey backward through time preserved within the frozen layers. One of the reasons ice cores are so valuable is because they preserve environmental information continuously across long periods. Many historical records created by humans cover only a small fraction of Earth's climate history. Written records may span a few thousand years at most, while glaciers preserve evidence stretching beyond human civilization. The deeper scientists drill into ancient ice, the farther back they can study conditions from distant ages. Within the ice cores, scientists examine dust particles, trapped gases, volcanic ash, isotopes, chemical compounds, and seasonal layering patterns. Together, these details reveal changing temperatures, atmospheric composition, storm activity, and conditions across enormous stretches of time. By comparing information from different ice layers, researchers can identify repeating climate cycles and major environmental events preserved within the glacier. Some volcanic eruptions discovered in ice cores were so large that they affected climate across the entire planet. Ash and sulfur particles from these eruptions settled onto glaciers and remain preserved within the snow layers. Scientists studying the cores can identify these volcanic signatures thousands of years later and estimate when the eruptions occurred. In some cases, ice cores provide evidence for eruptions that happened before written historical records existed anywhere on Earth. The annual layering preserved within many glaciers allows scientists to build highly accurate timelines. Seasonal differences in snowfall, chemistry, and dust create repeating patterns similar to tree rings. Researchers count these layers carefully to estimate the age of different sections within the ice. Deeper layers become progressively older, creating a chronological archive extending through repeated glacial and warmer periods in Earth's climate history. Ice cores from Greenland and Antarctica are especially important because the ice sheets in these regions have remained stable enough to preserve extremely old records. Antarctic ice cores in particular contain some of the longest continuous climate records ever discovered. These frozen archives reveal repeated cycles of colder and warmer conditions spanning hundreds of thousands of years. The data preserved inside the ice transformed scientific understanding of how Earth's climate system changes over time. Researchers also compare ice core information with evidence gathered from oceans, sediments, cave formations, tree rings, and fossil records. Together, these different sources help scientists build a more complete picture of past conditions. The glaciers act as one part of a much larger scientific effort to understand how climate systems have behaved across Earth's history and how different natural processes remain connected. The information preserved inside glaciers has practical importance beyond historical curiosity. By understanding how glaciers and climate systems responded to past changes, scientists gain insight into how modern conditions may continue evolving over time. Ice cores help reveal how temperatures, greenhouse gases, sea levels, and ice coverage interacted during previous climatic shifts. This knowledge improves scientific understanding of long-term environmental patterns operating across the planet. Glaciers function as natural archives created by nature. No human civilization intentionally recorded these ancient atmospheric conditions or climate patterns. Instead, snowfall quietly accumulated each year while trapping dust, gases, and environmental evidence inside the ice. The glacier preserved this information automatically through ages until scientists eventually learned how to read the frozen record hidden beneath the surface. Although glaciers may appear permanent and unchanging, they are actually highly sensitive to the conditions around them. Small shifts in temperature, snowfall, wind patterns, or seasonal weather can gradually influence how glaciers behave over time. A glacier survives only when enough snow accumulates to replace the ice lost through melting, evaporation, or the breaking away of icebergs. When that balance changes, the glacier begins responding almost immediately, even if the visible effects unfold slowly across many years. One of the most important factors affecting glaciers is temperature. In colder conditions, snowfall may continue building layer after layer, while relatively little ice melts away during warmer seasons. Under these circumstances, glaciers can gradually expand outward across the land. If temperatures rise over time, however, melting may begin removing more ice than snowfall replaces. When this happens, glaciers slowly shrink and retreat uphill or back toward colder regions. The process of glacier retreat often unfolds gradually enough that people living nearby may not notice the changes immediately. A glacier may lose only a small amount of ice each year, yet over decades, the difference becomes dramatic. Historical photographs taken many years apart often reveal glaciers that once filled entire valleys, but have since retreated far uphill, exposing bare rock and newly formed lakes where thick ice once existed. In some mountain regions, glaciers that remained relatively stable for centuries have changed noticeably within only a few human generations. Snowfall plays an equally important role in glacier survival. Even very cold regions may struggle to maintain glaciers if insufficient snowfall occurs each year. A glacier depends upon fresh accumulation in its upper regions to replace the ice continually moving and melting farther below. Reduced snowfall weakens the glacier's ability to maintain its size. Over time, even small reductions in annual snowfall can slowly shift the balance toward glacier retreat. Scientists often describe glacier health using the idea of mass balance. If a glacier gains more ice through snowfall than it loses through melting and other processes, it experiences positive mass balance and may grow larger. If the glacier loses more ice than it gains, it experiences negative mass balance and gradually shrinks. This balance acts almost like a long-term environmental scale, responding continuously to climate conditions surrounding the glacier. Some glaciers respond relatively quickly to environmental changes, while larger ice sheets may react much more slowly because of their enormous size. Small mountain glaciers can change visibly within decades as temperatures and snowfall patterns shift. Massive polar ice sheets respond over much longer timescales because the ice is so thick and extensive. Yet even these enormous systems remain sensitive to gradual climatic changes unfolding over centuries. As glaciers retreat, they often leave behind newly exposed landscapes that may not have seen sunlight for thousands of years. Bare rock, fresh sediment, and recently uncovered valleys emerge from beneath the ice. Plants gradually begin colonizing the exposed terrain. Streams and lakes form where meltwater collects. Entire ecosystems slowly develop in areas that were previously buried beneath moving glaciers during colder climatic periods. Retreating glaciers can also create unstable conditions in some regions. Meltwater lakes forming near glacier edges may grow large behind natural ice or sediment barriers. If these barriers fail suddenly, powerful floods can rush downstream through mountain valleys. In polar regions, glaciers flowing into the ocean may release large icebergs as sections of ice break away from the glacier front. These natural processes have always occurred to some degree, though changing climate conditions can influence how frequently they happen. Not all glaciers are shrinking at the same rate. Some glaciers remain relatively stable, while a few continue advancing because of local snowfall and temperature conditions. Climate systems vary greatly across different regions of the world. A glacier in one mountain range may retreat rapidly, while another glacier elsewhere changes much more slowly. Scientists therefore study many glaciers across different environments to better understand broader climate patterns affecting ice coverage around the planet. Glaciers also influence the environment surrounding them as they change. Mountain communities in some regions depend heavily upon glacier meltwater for drinking water, farming, and hydroelectric power. Seasonal melting from glaciers feeds rivers during warmer months, especially in areas where rainfall alone would not provide enough water. Changes in glacier size can therefore affect freshwater supplies beyond the glacier itself. The response of glaciers to environmental change provides scientists with valuable evidence about long-term climate trends. Because glaciers react gradually but consistently to temperature and snowfall patterns, They act almost like natural indicators, showing how climate conditions evolve over time. Measuring glacier movement, thickness, and retreat helps researchers track environmental changes occurring across mountain ranges and polar regions around the world. Over long periods of observation, glaciers reveal just how closely they respond to changes in their surroundings. A glacier may appear stable during a short visit, yet measurements collected across decades often show gradual shifts in thickness, movement, and overall size. Scientists who monitor glaciers return to the same locations each year to measure how far the ice advances or retreats, how quickly it flows, and how much snow accumulates across the surface. These observations provide valuable insight into how glaciers react to changing conditions over time. One of the clearest signs of glacier change can be seen at the glacier's edge, often called the terminus. In colder periods with strong snowfall accumulation, the glacier may slowly advance downhill as more ice moves forward than melts away. During warmer conditions, the terminus may retreat uphill as melting exceeds the arrival of new ice from above. Historical records, old photographs, satellite images, and direct field measurements all allow scientists to compare how glaciers have changed across many decades. In some mountain regions, glaciers that once filled entire valleys have gradually withdrawn far into higher elevations. Exposed rock, newly formed lakes, and fresh sediment now occupy areas that were once covered by thick ice. Vegetation slowly spreads across terrain uncovered by retreating glaciers. Mosses and grasses appear first, followed by shrubs and eventually forests in some environments. The changing glacier leaves behind a landscape that continues evolving long after the ice moves away. Glaciers reflect conditions because they respond directly to temperature, snowfall, wind, and seasonal weather patterns. A colder period with heavy snowfall may increase glacier growth and movement. Warmer temperatures may increase surface melting and reduce the glacier's overall mass. Strong winds can redistribute snowfall across the glacier surface, influencing how accumulation occurs in different areas. Every glacier, therefore, acts as part of a larger environmental system connected closely to the climate surrounding it. Scientists sometimes describe glaciers as environmental indicators because changes in glacier behavior often reveal broader shifts occurring within climate systems. Unlike short-term weather events, glaciers respond gradually to long-term trends unfolding across many years. Measuring glacier retreat, growth, or movement provides researchers with important evidence about conditions operating across mountain ranges and polar regions. Modern technology has improved the ability to observe glacier change. Satellites orbiting high above Earth can measure glacier movement, surface elevation, and ice coverage across enormous regions. Aircraft equipped with radar systems map the thickness of glaciers and ice sheets beneath the surface. Researchers place instruments directly onto glaciers to track movement, snowfall, temperature, and melting throughout the year. Together, these methods allow scientists to monitor glaciers with far greater detail than was possible in the past. Some glaciers respond dramatically to seasonal changes. During warmer months, surface melting may increase the amount of water flowing beneath the glacier. This meltwater can temporarily increase glacier movement by lubricating the base of the ice. During colder seasons, movement may slow again as surface melting decreases. Other glaciers change much more gradually because of their size or colder conditions. The behavior of each glacier depends upon a complex interaction between climate, terrain, snowfall, and internal ice dynamics. Glacier change also influences surrounding ecosystems and landscapes. Meltwater from glaciers feeds rivers, lakes, and wetlands used by plants, animals, and human communities. As glaciers shrink or expand, water availability may shift throughout nearby regions. Newly exposed land becomes available for colonization by vegetation and wildlife. In polar regions, changes in glacier flow can influence ocean circulation and iceberg production along coastlines. Despite their immense size, glaciers remain surprisingly dynamic systems. Ice constantly flows downhill under gravity. Snowfall adds new material to the upper glacier. Melting removes ice from lower sections. Cracks form and close within the ice as pressure changes over time. Hidden rivers flow beneath the glacier surface. Large sections may occasionally fracture and break away into the sea. The glacier continuously adjusts itself in response to changing conditions, even when the overall movement appears extremely slow. Scientists studying glaciers have learned that no glacier remains entirely static forever. Some glaciers advance for centuries before retreating again. Others shrink steadily for long periods before stabilizing under new climate conditions. The frozen landscape changes continuously through a balance of accumulation, movement, erosion, melting, and deposition, operating together over time. This dynamic behavior helps explain why glaciers remain important in climate research. Because glaciers respond directly to conditions, they preserve valuable evidence about how Earth systems behave across long timescales. Ice records past climates deep within its layers, while the glacier itself continues reacting to present conditions at the surface. In this way, glaciers connect the environmental history of the past with the changing climate of the present. Glaciers exist at the intersection of many natural systems. They connect climate, geology, water, atmosphere, and time through processes that unfold continuously across the Earth. Snow falls from the atmosphere onto mountain peaks and polar plains. That snow slowly compresses into dense ice. Gravity pulls the ice across the land where it reshapes valleys, transports sediment, and alters rivers and coastlines. At the same time, the glacier preserves records of ancient climates deep within its frozen layers. Few natural features reveal the interconnected nature of Earth's systems as clearly as glaciers do. The movement of glaciers links climate directly to the land itself. During colder periods, glaciers expand and advance across mountains and plains. As the ice moves, it grinds against rock surfaces, deepens valleys, and carries enormous amounts of sediment across great distances. During warmer periods, glaciers retreat and expose newly shaped landscapes beneath the melting ice. The terrain visible today in many regions reflects thousands of years of interaction between climate conditions and moving glaciers. Every glacier also acts as a record of environmental history. Layer after layer of snowfall preserves information about atmospheric conditions from the time the snow originally fell. Dust, volcanic ash, trapped gases, and chemical particles become sealed within the ice as glaciers slowly grow. Deep beneath the surface, ancient snowfall remains preserved from climates long before recorded human history. The glacier therefore functions both as an active geological force shaping the Earth and as a frozen archive preserving evidence of the planet's changing environment. The relationship between glaciers and their surroundings never fully stops. Fresh snowfall continues adding new material to the glacier surface. Ice slowly flows downhill under pressure and gravity. Meltwater moves through cracks and hidden tunnels within the glacier. Sediment becomes trapped inside the ice and later deposited across the land. Wind carries dust onto the glacier, while sunlight influences surface melting. Every part of the glacier remains connected to broader environmental processes unfolding around it. Even the oceans are linked closely to glaciers. Large ice sheets store enormous quantities of frozen water on land. During colder glacial periods, sea levels fall because so much water remains trapped inside expanding glaciers and continental ice sheets. During warmer periods, melting glaciers return water to the oceans and sea levels rise again. Coastlines shift gradually as the balance between frozen water and ocean water changes across long climatic cycles. Mountain glaciers also influence freshwater systems across many parts of the world. Rivers fed by seasonal glacier melt supply water for forests, wetlands, farms, wildlife, and human communities. In some regions, glacier meltwater remains critically important during dry seasons, when rainfall alone would not provide enough water. The changing behavior of glaciers therefore affects not only remote polar environments, but also ecosystems and populations far downstream. The geology beneath glaciers influences how the ice moves and reshapes the landscape. Softer rock may erode more easily beneath the glacier, while harder rock resists erosion for longer periods. Valleys guide glacier movement downhill through mountain ranges. Fractures in bedrock influence where plucking occurs. The glacier shapes the land, while the land itself influences the glacier in return. Over long periods, this interaction gradually transforms regions. Glaciers also reveal the immense scale of geological time. Human history occupies only a very small fraction of the periods preserved inside deep glacier ice. Entire civilizations rise and disappear, while glaciers continue advancing, retreating, and storing new environmental layers each year. Snowfall from ages before agriculture, before written language, and before modern coastlines still remains preserved beneath the surface of Antarctica and Greenland today. Scientists studying glaciers often describe them as natural archives because they preserve such detailed records across enormous spans of time. Yet glaciers are not passive archives sitting unchanged in the landscape. They remain active systems constantly responding to surrounding conditions. Ice flows, pressure changes, cracks open and close, snow accumulates, meltwater moves beneath the glacier. The frozen landscape continues evolving continuously, even while preserving ancient history within its deeper layers. The connection between glaciers and climate becomes especially clear when studying long-term environmental cycles. Colder climates allow glaciers to expand and reshape the land more extensively. Warmer climates reduce ice coverage and expose terrain previously buried beneath glaciers. The changing size of glaciers therefore reflects larger shifts occurring throughout Earth's climate system. By studying glaciers, scientists gain insight into how atmosphere, oceans, land, and ice interact across long periods. From the first snowfall settling quietly onto cold ground to the deepest layers preserved beneath polar ice sheets, glacier processes never fully stop. Snow compresses into ice flows downhill, sediment moves within the glacier, Valleys deepen beneath the moving ice. Ancient air becomes trapped inside frozen bubbles. Meltwater carves tunnels beneath the glacier surface. Every stage remains connected to the broader environmental systems surrounding the ice. The remarkable thing about glaciers is how many parts of the Earth they connect together at once. They shape mountains and valleys through movement. They influence rivers and oceans through melting. They preserve atmospheric history inside ancient ice. They respond to climate shifts, while also recording evidence of those same changes deep within their layers. Glaciers reveal how closely connected Earth systems truly are across the immense timescales of geological history. Far beneath the frozen surface, ancient snowfall still rests where it settled long ago. Above it, fresh snow continues falling onto the glacier each year. The cycle continues quietly through passing centuries as glaciers preserve the memory of the past while remaining active parts of the changing world around them. Across Earth's surface, glaciers have quietly shaped the landscape for immense stretches of time. Mountains, valleys, lakes, coastlines, plains, and deep fjords all preserve evidence of moving ice that once passed slowly across the land. Some glaciers remain active today in mountain ranges and polar regions, while others disappeared thousands of years ago after ancient ice ages came to an end. Yet even where the ice has vanished, the marks left behind continue revealing how powerfully glaciers transform the Earth through movement, pressure, erosion, and time. The influence of glaciers can be seen in places beyond the frozen regions where they exist today. Broad valleys once carved by glaciers now contain forests, rivers, towns, and cities. Fertile farmland stretches across plains built from glacial sediment deposited long ago. Lakes formed by retreating glaciers supply water to ecosystems and human communities across many countries. Roads and railways follow pathways first opened by ancient ice, moving through mountains thousands of years earlier. In many ways, modern landscapes still carry the hidden influence of glaciers, even in regions where no permanent ice remains. Climate has always played a central role in glacier formation and change. During colder periods, glaciers expand gradually as snowfall accumulates faster than melting removes ice. During warmer periods, glaciers retreat as temperatures rise and melting increases. These cycles have repeated many times throughout Earth's history, slowly reshaping continents and altering sea levels across ages. The glaciers preserved records of these climatic shifts deep within their frozen layers, while also responding directly to the changing environment around them. The relationship between glaciers and climate reveals how connected Earth systems are. Snowfall depends upon atmospheric conditions. Ice movement depends upon gravity, temperature, and terrain. Meltwater influences rivers, oceans, ecosystems, and sea levels. Expanding glaciers reshape landscapes, while retreating glaciers expose new terrain to sunlight, weather, plants, and animals. Every stage of glacier activity connects to broader environmental processes unfolding across the planet. One of the most extraordinary things about glaciers is the way they preserve time itself. Deep inside the ice, ancient snowfall remains frozen exactly where it settled long ago. Tiny air bubbles still contain traces of atmospheres from distant ages. Dust from ancient storms, ash from volcanic eruptions, and chemical evidence of long-vanished climates remain sealed within the glacier layers. The ice quietly stores environmental history across timescales far older than human civilization. Scientists drilling into glaciers today are therefore studying both the past and the present at the same time. The deeper layers reveal climates from hundreds of thousands of years ago, while the glacier surface continues responding to modern conditions. Ancient records remain preserved beneath the ice, while snowfall, melting, movement, and climate change continue shaping the glacier above. Few natural systems connect past and present so clearly across such enormous spans of time. The immense patience of glaciers may be the most remarkable thing about them. Rivers may flood suddenly. Storms may transform coastlines within hours. Forests may grow and disappear over centuries. Glaciers operate on timescales so vast that their movement often feels almost beyond ordinary human experience. Yet every moment, deep inside the ice, the processes continue. Snow compresses into dense glacier ice. Gravity pulls frozen rivers slowly downhill. Rocks scrape against the earth beneath the glacier. Ancient air remains trapped inside frozen bubbles. Layer after layer continues building quietly beneath the surface. In remote polar regions, glaciers still stretch outward across frozen landscapes beneath pale sunlight and drifting snow. In mountain valleys, rivers of ice continue winding slowly between steep cliffs shaped by erosion over countless generations. Hidden tunnels carry meltwater beneath the glaciers, while cracks open across the surface under shifting pressure. Far below, ancient layers remain sealed inside the ice, preserving environmental records from climates long before modern history began. Even after glaciers retreat, the landscapes they shaped continue telling their story. U-shaped valleys, polished rock surfaces, scattered boulders, moraines, fjords, and glacier-fed lakes all remain as evidence of moving ice from distant ages. The earth itself preserves the memory of glaciers within the shape of the land. Mountains and valleys carry the marks of processes that unfolded slowly across thousands of years beneath enormous frozen sheets of moving ice. The hidden world of glaciers is therefore not only a story about frozen landscapes, it is also a story about climate, geology, water, atmosphere, and time itself. Glaciers reveal how slowly the Earth can change and how powerfully natural systems shape the planet across deep history. They remind us that landscapes often considered permanent are actually part of long, continuous processes unfolding quietly over generations. Far beneath the ice, ancient snowfall still rests where it first settled onto the glacier long ago. Above it, fresh snow continues falling during each passing winter. The glacier flows onward slowly beneath the force of gravity, while preserving the environmental memory of the world around it. Ice continues shaping the Earth, just as it has for countless ages before. Thank you for listening to the Sleepy Mind channel. I hope you enjoyed learning about the hidden world of ice and glaciers. Good night.